So, hello everyone. Good evening to all. My name is Abhishek Pandey. I'm a Prime Minister Research Fellow in the discipline of mathematics at IIT Bhubaneswar. Today we are going to talk about week 4 assignment. Uh, so, so the content for week 4 is harmonic mappings, uh, a Mobius transformation, extended complex plane, and curves in complex plane. Okay, so we will first recall these facts and then we will see the assignments based upon this one. Okay, so let us start. Okay, so let us first see the extended complex plane via as a compactification. Uh, it is so we are seeing extended complex plane as S2. So it is kind of a compactification of extended complex plane. Okay, so this is also known as stereographic projection. So take a sphere and a plane passing through middle of it, and just consider this N north pole. So any point P belongs to S2 minus this north pole, line joining N and P. Okay, so you take any point P on the wait a minute, it is not moving. Yeah, so so once you draw a line and join a point on the plane, so this will intersect at a point P on the sphere. Okay, and we call it as phi of P. Okay, so this one is an homeomorphism S2 minus north pole, and similarly you can do with the south pole. Okay, so this is the stereographic projection. Okay, so like so this is the general case Sn, it is Rn union infinity. So we will only talk about this thing in plane, that is n equals to 2. Okay, so what would be the formula for this function? Okay, like phi of let us say phi of this point. So phi of any point of this will be the intersection point on this P. Okay, so okay, so define the stereographic projection to the map like sigma. So it will send x to u. Okay, so where u is nothing but u comma 0 in Rn plus 1. Okay, so so it is kind of S3. So we are choosing, so we are just projecting in the plane. So we are taking the third component z as 0. Okay, so we need to find out the formula for this function. Okay, so line through n and x meets the subspace where xn plus 1 is 0. So basically it is so you take n equals to 2, so it is basically line through n and x. Okay, so meets the subspace where x3 is 0. Okay, so x1 x2 x3 x3 is 0. So formula for sigma of x is equals to u is characterized by like vector equation. So it is u minus n is equals to uh, lambda x minus n for some real number delta. Okay, so this is nothing but the equation of line in Rn plus 1. So this is equation of line in R3 joining n and x. So what we are doing is it is kind of it is kind of we are just it is kind of we are taking a point on the plane and and we are taking the line joining this point in the plane to the north pole. So it will hit the sphere at some point, that is point that is called x. So we are calling an sigma of x is equals to u. So u is in the R2. Okay, so this is the equation of line. Okay, now you just have to, so x is of this form, n is of this form. Now you just have to calculate and you will get the basically, so this is the system of linear equation where ui is equals to lambda xi and lambda xn plus 1 minus 1 is equals to minus 1. So you just need to get the form of lambda and ui So just remember what we are doing. So what we are doing is we are getting this. What would be this function? How this function maps x to u? Okay. Okay. So this is kind of yeah. Okay. So we need to get what would be this point x where it hits the. We need the coordinate of x where it hits the sphere. So it is. So this will be basically sigma inverse u. So sigma inverse u is nothing but u1, u2, un. So we will just consider u1, u2. So this in R2 we will consider u1 comma u2, complex plane u1 plus I u2. So this will be of this form: 2 u1 comma and so on to un comma u mod u square minus 1 and 1 plus mod u square. Okay. So this is the formula for the stereographic projection. Okay. And similarly, you can do it for south pole also. So S2 minus this north pole is homeomorphic to Rn. Okay. So okay. So R2 we have taken. So you take the plane R2. So this is your sphere. Okay. So S2 minus the north pole is basically covering the R2, which is homeomorphic. And once you tends to and once you tends to infinity in R2, this lines these intersection points will tend to the north pole. So basically we are attaching north pole to infinity. Okay. So this whole S2 will be known as uh, R2 union infinity, means C union infinity. So it is a compactification of the complex plane. So it is a sphere. Okay. Yeah, fine. So next we will talk about the Mobius transformation. So it is simple. It is there in the notes and also many books you can find it out. So it is a rational function of this form Az plus b upon Cz plus d, where A, B, C, D belongs to complex plane and AD minus BC is non-zero. Okay, where T is analytic on C minus D minus C. Okay, this is easy to see. Okay, so this we will talk about later. First, let us see. Okay, so Mobius transformation can always be written. Yeah, so Mobius transformation can always written as a composition of these functions. So it is. So this is basically translation. Okay, so this is basically translation, and this thing w2 equals to 1 upon w, this is the thing with the inversion, this is again a translation, and this w3 will depend upon whether it is magnification or stretching. Okay. So this will be the magnification or stretching. Yeah, so it will depend how it will be magnification or rotation. So rotation is basically z going to z e to the I theta, theta belongs to r, so this modulus will be 1. And stretching and magnification, or so stretching or contraction, this will depend upon this one r and this one. Okay, so it is of this form rz. So depending upon this one, depending upon this quantity minus AD minus BC upon C square, whatever the value is, this will be known as whether it is shrinking or contraction. Okay. Yeah, so let us move ahead. Yeah. So as we can see, the T is 1 1 on C minus D minus C. This is easy to see. This Mobius transformation is 1 1, and so hence it is analytic. T and T inverse is analytic from C minus D minus C to C minus A minus C. Okay, so once you attach minus D minus C, so it will be from C infinity to C infinity. So just you have to take the infinity as a number here, like it is mapping minus D minus C to infinity. Okay, so T of minus D minus C equals to infinity and T of infinity equals to infinity if C is 0. Okay, so basically it becomes the T is a bijection between extended complex plane C infinity onto itself. Okay, so T maps Riemann sphere onto itself. So it is kind of an automorphism of, so biholomorphic map from C infinity to C infinity. So inverse of a Mobius transformation is also a Mobius transformation. Composition of two Mobius transformation is also a Mobius transformation. Okay, so these two things. Yeah. Okay. So yeah, so some important facts about the inversion map. So it is a map of this form, z going to 1 by z. So it has some properties. So the image of a line through the origin is a line through the origin, and the image of a line not through the origin is a circle through the origin. The image of a circle through the origin is a line not through the origin. So the image of a circle not through the origin is a circle not through the origin, and like it maps upper half plane to the lower half plane, and the right half plane is mapped to itself, and left half plane is mapped to itself. Okay, so this is the properties of so this inversion map is quite important. Also, how it maps to circles, this is quite important. So points on the circle, this circle center at 0 and radius r are mapped points on the circle 1 by r, and the disk is mapped to the disk, this one. Okay, so this is just a calculation formula, and you can just calculate. So image of certain sets under inversion. So these are all, so these things, so these all things are in the notes, you can go through later on. Okay, so yeah, this is the property. So let T be a so this you can consider as a one problem. So let T be a Mobius transformation other than the identity, then T has at most two fixed points. Okay, so we will divide this in several cases. Uh, so if so Tz is equals to Az plus B upon Cz plus D, where Ad minus Bc is non-zero, is such that T of Z is equals to Z for every Z belongs to C, then Tz equals to Z implies, so this is how we calculate the fixed points. So this is the root. So this is the solution of this one, roots, fixed points. So Az plus B equals to Cz square plus ds. So Cz square plus D minus Az minus B equals to 0. So it is, if C is non-zero, this is again a quadratic equation, and you will get two roots, okay, or at most two roots. And similarly, if C is 0, then again you will get so it will, at most it will have two roots. Okay, but yeah, but one more thing, because infinity also we are including in this one, so we have to be precise here, and we have to be careful. So if C is non-zero, then T of minus D by C is equals to infinity. So infinity and minus D by C cannot be a fixed point, and then this has two roots. Okay, so this T has two fixed points. Again, if C is equals to 0, then T maps infinity to infinity. So infinity is a fixed point, and this is again a linear map Az plus B. So it is again have one root. So again this has two roots. So it has two fixed points. If C is 0, again C is 0, B is non-zero, A is equals to D. So infinity is the only fixed point. So this you can just calculate. Okay, fine. These are things. These are in the notes, and if you want a detail on this one, you can go through the Conway book. I will just mention what are required for the for the for the assignments. Okay. So these things you can go through the notes. We will. Yeah, so this is one more thing. So circles in the extended complex plane. So circles in C infinity. So we refer circle in C infinity to a subset subset of C infinity. That is, it is either a circle in C or a circle through infinity, means a line. Okay, so L union infinity. So L union infinity and a proper circle in C. This we call as circles in extended complex plane. So Mobius transformation maps circles onto circles in C infinity. Okay. Yes. Okay, so these are the notion of curves in complex plane. Okay, so let's C comma D be a metric space again. So a continuous function is called a curve, and the length of the curve is denoted by this. So if you have a curve, so curve in complex plane means it's a continuous function from this compact interval to C, and the length of the curve is denoted by this. So supremum over P, so P are the partitions, and gamma of Tk minus gamma Tk plus 1, k equals to 0 to n minus 1. So in the complex sense, if you see, so it is kind of dz equals to dx plus I dy. You can take the modulus dz and you can just calculate the integral of mod dz over gamma, and this is nothing but this will give you the length of the curve. So for that, your gamma should be continuously differentiable curve. So means if gamma is a continuously differentiable curve, then gamma is rectifiable. So rectifiable means this length here, this length here. Uh, so this length here should be less than infinity, means it should be finite. So if gamma is continuously differentiable, you can just calculate this length of the curve by this integral. Okay. So this one, integral over a to b gamma dot t dt. Okay. Even if it is piecewise continuously differentiable, then also you can calculate. So these are the basic facts about this one. So these are the properties of the curve. Okay. So so this is the change of variable formula. So how do we integrate? So if suppose f is a continuous function on this curve, okay, so so what would be the line integral of this f? So integral over gamma f of z dz is equals to integral a to b f of gamma t into gamma dot t dt. Okay, so here dt should be there. Okay, so this is the way we calculate the length of the curve. Again, this is just a summary of Mobius transformations. Yeah, so this is some properties. Composition of two Mobius transforms, again a Mobius transformation. Mobius transforms are one-to-one mappings. Inverse is also Mobius transformation. Other things. So Mobius transformations are conformal, analytic, and one-one. Mobius maps are automorphisms of C infinity. Okay. Okay, so this is the matrix representation of Mobius transformation. So the coefficient of Mobius map can be represented by a matrix. Okay. So A is equals to A, B, C, D. This is general linear group. For any Mobius transformation M, so ZL2C is basically this one, where determinant of A is non-zero. Okay, so this map defined by A, B, C, D to AZ plus B upon CZ plus D is a homomorphism. Okay. Any Mobius transformation can be represented by this metric in SL2C. So we'll just parameterize it. So determinant of A is equals to 1. So T can be represented by A, B, C, D. This is in this one. Now you again divided by determinant. So you will get this one, and this will be again SL2C. Okay. So this part we will see later. Okay. This is the context. This is the thing for later. Okay, so now we will move towards the problem. So this is related to the harmonic functions. So which of the following statements are true? So the function is u of x comma y is equals to x minus 2 upon x square plus y square minus 4x plus 4 is harmonic on the open connected subset, this one. Okay. So we will check whether this is harmonic in this one or not. So u of xy is equals to this. So what we will do is that x minus 2 upon x minus 2 whole square plus y square is basically a real part of this one. Okay. So this is nothing but x minus 2 whole square plus y square. So this is just an observation. So it is a real part of this one. And so we will get that real part of 1 upon z minus 2 by calculating. Okay. So now 1 minus z by 2, 1 upon z minus 2 is holomorphic in this domain. Thus u is harmonic since it is a real part of a holomorphic function. Okay, so what is the next problem? Let f and z be two holomorphic functions defined on an open connected set omega such that real part of fz is equal to real part of zz. For every z belongs to omega, then fz is equal to zz for every z belongs to omega. Okay, so now let us consider a function hz is equal to fz minus gz. So real part of fz is 0 for every z belongs to omega. So this implies that s dash z is 0. So it means that fz minus gz is a constant. Okay, so it is fz is equal to gz plus k. Okay. So yeah, so real part of fz minus real part of gz is gz are equal. So real part of hz will be 0, means real part of k is equal to 0. That is, k is purely imaginary. Okay, so this fz is nothing but gz plus something I into m. Okay, so what we will get? So fz is equals to gz plus I into something. So this is not true. Okay, fz is not equal to gz, but some translation of this one with purely imaginary constant. Okay, so let f, yeah, so this is true now. Third one, so let f and z be two holomorphic functions. Define an open connected subset such that real part of f is equal to real part of z for every z belongs to omega. Then fz minus gz is a purely imaginary constant on omega. This we just proved. The harmonic conjugate of a given harmonic function u on omega is unique. This is also not true. So harmonic, yeah. So harmonic conjugates are unique up to adding a constant. Okay. So they are not in general unique, but they are unique adding up to constant. So this is a standard fact. So let v and w are two harmonic conjugates of u. Then I into w minus v is equals to this one is holomorphic. So because w is harmonic conjugate, so this is holomorphic. Because w is so this is holomorphic, and again v is harmonic conjugate, so this is holomorphic. So this difference between two is holomorphic. And since this is purely imaginary, why this is purely imaginary? Because this w and v are two harmonic conjugates of u. So this is nothing but obviously this is nothing but a real only. So you just multiplying with I. So this will be purely imaginary and holomorphic. So it must be a constant. Okay. And thus we get w is equals to v plus a for some a belongs to c. Okay. Okay, so what is the next problem? So what is the next option? Yeah. So let v be harmonic conjugate of harmonic function u such that u minus v is constant. Okay, so v is a harmonic conjugate of a harmonic function u on omega such that u minus v is constant. Then it is asking whether u is constant or not. Okay, so let v be a harmonic conjugate of u on omega such that u minus v is constant. So f is equals to u plus iv is holomorphic on omega, and if is again also holomorphic on omega. So f plus if is nothing but u minus v plus I u plus v is also holomorphic. And this thing u minus v is constant. Sorry, this thing is constant, u minus v. So u minus v is equals to k1 belongs to c. So f plus if is becoming constant, and so u plus v is equals to k2. Means this is also constant. So by equation 1 and 2, so this is 2, we have u is equals to k3. Okay, so we will get that u is also constant. So this is simple. Okay, yeah. So this first thing is just a calculation. So let let GL2C denote the group of all immutable 2 cross 2 matrices. In particular, observe that if alpha is equal to this, so this just I mentioned earlier regarding the matrix representation of a Mobius transformation. So this is defined on the extended complex plane. Which of the following statements are true? Okay, so first thing is if alpha comma beta is in GL2C, then alpha dot beta dot z, so this is composition of this one, is equals to alpha beta of z. Okay, so this is just a calculation, it is true. Just one has to verify this one. So alpha dot beta dot z is equals to alpha of this one. So alpha is this, so you have to just remember that how it is defined. Alpha of z is nothing but, so alpha is this, alpha of z is nothing but again giving the Mobius transformation. So this is just a function. Okay, Second thing is 2 alpha into z is equals to 2 into alpha into z. So this basically, this will be 2 alpha is equals to 2a, 2b, 2c, 2d, and 2 alpha of z is nothing but it is, so 2az plus 2bz, 2az plus 2b upon 2cz plus 2d. So this 2 will be cancelled out. This is again az plus b, and so this will be alpha into z, not 2 into alpha. So this 2 will be this 2 will be not here. Okay, so let us see the next option. In particular, if alpha is in SL2R, that is matrices with a coefficient and determinant 1, then imaginary part of alpha into z is positive if and only if imaginary part of z is greater than 0. Okay, so this is just a reference I have mentioned here. So this is let alpha belongs to SL2R. So this is the definition, and alpha into z will be this, and let this one h plus. So this is upper half plane. So alpha into z maps h plus onto itself. So there is a theorem, az plus b upon cz plus d maps upper half plane onto itself if and only if this ABCD belongs to R and AD minus BC is positive. So you can just go through these two books, Conway and Bruce P. Palka. Okay, so next thing is, suppose that imaginary part of z is positive, then there exists an alpha, this one says the alpha into y is equals to z. Okay, yeah, so this is basically, okay, so this is basically the transitive group action. So let me denote something here. So let us recall a group action. So let x be any set and g be a group. We say that g acts on x if there is a binary operation g dot x to x satisfying 1 dot x is equals to x for every x belongs to x, and gh dot x is basically g and h dot x. So h dot x will again go into x, and so this will be g dot, okay, for every g comma h belongs to g. So given such an action, define a relation on x. So x is related to y if there exists a g belongs to this capital G such that y is equals to g dot x. Okay. So this is an equivalence relation. So what we call an orbit is nothing but, orbit of x is nothing but collection of all g such that we will take g dot x. Okay. So you just take g and operate g dot x, operate it on x. A stabilizer of an element is x belongs to nothing but, so stabilizer of x is nothing but collection of all those g's belongs to capital G, which gives x again, operating on x gives x. Okay, so g dot x is equals to x. An action of a group G on a set X is said to be transitive if it has a single orbit. It means that you take any 2 points belongs to X. There is a group element G such that G dot X is equals to Y. Okay, so means every 2 are related to each other by this action. Okay, now the thing is, okay, so the thing is SL2R acts on H in H plus, okay, via this one. So you take SL2R acts on H plus and define this binary relation alpha dot Z is equals to AZ plus B upon CZ plus D. So this again belongs to H plus as we have seen earlier. Okay. Okay. Okay, so claim there exists alpha belongs to SL2R such that alpha dot I is equals to Z. Okay, so for Z, for any Z, this, and you take alpha is equals to this one, root over y, x upon root over y, 0, 1 upon root y. This will belongs to SL2R. You can just calculate so that this one. Now inverse or alpha will take Z to I. So claim SL2R acts transitively on H plus. That is for every Z1 comma Z2 belongs to H plus upper half plane. There exists alpha belongs to SL2R such that alpha dot Z1 is equals to Z2. Okay, so let alpha 1 belongs to this SL2R such that alpha 1 dot Z1 is equals to I. So Z1 is going to I. Okay, and alpha 2 dot I is equals to Z2. Okay, I is going to Z2. Now take alpha is equals to alpha 2, alpha 1. Okay, this. So alpha dot Z1 is equals to alpha 2 dot alpha 1 dot Z1. This is nothing but alpha 2 dot I, because this alpha 1 dot Z1 is I. Now alpha 2 I is equals to Z2. So how we are able to do this one? Like we can find a map alpha 1 which can send Z1 to I, and we can find a map alpha 2 which sends I to Z2. This is because of this above fact. Okay, so for any Z you can find alpha, okay, such that alpha dot I will be Z, and similarly you will take the inverse of alpha that will send Z to I. So here for Z1, so for Z1 you take alpha like this, so that will send I to Z1, and for Z2 again you will take the inverse of that. Okay, so this we can done. So this we can do easily. So alpha dot Z1, now this alpha dot Z1 is clearly Z2. So SL2R acts transitively on the upper half plane. Okay, so this is fine. Let us look at the last option. Okay, again we have to go back. Yeah, so alpha belongs to SL2R is such that alpha dot I is equals to I, then there exists a real number theta such that this happens. So this is based upon a calculation. Okay, let's see. Yeah, so alpha belongs to SL2R such that alpha dot I is equals to I. So alpha is what? Alpha is A, B, C, D, such that AD minus BC is equals to 1. So that is AI plus B, CI plus D is equals to I. Now just calculate this one. So this one nothing but AI plus B is equals to DI minus C. Okay, so AI plus B is equals to DI minus C. And since alpha belongs to SL2R, therefore AD minus BC is equals to 1. Okay, so this, so what we will get? So you just compare the real and imaginary part here. Okay, so you will get A equals to D and B equals to minus C. So AD minus BC is what? AD is A square plus B square is equals to 1. Okay, so this is nothing but on the unit circle. So on unit circle you will get a theta such that A plus IB is equals to E to the power iota theta. Okay, so it means that A is equals to cos theta will be equals to sin theta for some theta belongs to this one. So alpha is equals to cos theta, sin theta minus sin theta and cos theta. Okay, so this thing is clear. So this problem is done. Okay, so now the next question is, so this is on the length of the curve. Let Z1, Z2, Z3 be three non-collinear points. Okay, and let gamma is equals to be the unique circle passing through this one, starting and ending at Z1. Okay, so this we know that with three non-collinear points we have a unique circle. Okay. Okay, so passing through this one, starting and ending at Z1. Let phi be the Mobius transformation that maps Z1, Z2, Z3 to 1, I and minus 1 respectively. Okay. Defined by phi o gamma, phi composition gamma, the curve defined by this one. Then what would be this? 1 upon 2 pi and this length of phi o gamma. So phi o gamma is the length of this phi composition gamma. Okay. So solution. So this is nothing but Z1 going to 1, okay, Z2 going to I, Z3 going to minus 1. So this is your Mobius transformation. Z3 is going to minus 1 here, Z2 going to I, and Z1 going to 1. Okay, so just take a rotation, Z1 to Z2, Z2 to Z3, Z3 to Z1. So 1 to I to minus 1, then again minus 1 to 1. Fine. Fact, Mobius transformation maps circles in C infinity onto circles in C infinity. Okay, so either a straight line in C, so this we know, circles either a straight line in C, element infinity, or circle in C. Okay, as we can see that phi o gamma is again a circle. You can see this one. Okay, center at 0 and radius 1. Therefore, the length of this phi o gamma is nothing but 2 pi, r is 1. So again upon 2 pi, so this will be 1. Okay, so this is quite simple. So it means that this phi can map the circle either onto circle or a line. So again we can say that this is again a circle. Okay, so this is easy to derive from here. Okay, now next question. Suppose that gamma such that 0 comma 2 log 10 to c is given by gamma of t is equal to 3 plus iota e to the power t. Then what would be the length of gamma? Okay, so length of gamma is nothing but integral over gamma mod dz, which is nothing but 0 to integral from 0 to 2 log 10 modulus of gamma dot t dt. Okay, this is simple. So integral from 0 to 2 log 10 base e iota e to the power t and dt. So what would be the so this one nothing but iota e to the power t only. Okay, so this will be modulus of iota will be 1 and e to the power t is again e to the power t because it is positive. So this will, so this integration we will get as 100 minus 1 is equals to 99. Okay, so this is done here. Yeah, so let us look at the last problem. So which of the following statements are true? Okay, so for simplicity we shall assume that all the curves considered are continuously differentiable. So this is for simplicity because so that there should be no problem of calculating the length. We can just directly apply the formula integral. So the length will be integral over gamma. Integral from a to b mod of gamma dot t dt. Okay, so yeah, observe that in particular, yeah, so if it is continuously differentiable, it means it is rectifiable because integral will be a to b mod of gamma dot t and dt. So this will be less than infinity. Okay, and we will denote it by the arc length of gamma. Suppose gamma 1 from AB to omega is a curve, and if this is a reparameterization of gamma 1, then image of gamma 1 and gamma 2 is in omega coincides. Okay, so this is just a fact. Okay, so let gamma 1 from AB to omega is a curve, and gamma 2 such that 0 1 to omega is a reparameterization. I hope that everyone has gone through all these facts, reparameterization of a curve and other things. Otherwise also I will try to include it in my notes. You can go through when I will upload on this one. Gamma, that is, so what is the reparameterization? That is, there exists a continuous function, continuous onto a non-decreasing function such that we have this one. So gamma 2 is attained by a composition of gamma 1 and h. So we are just reparameterizing this. For gamma 2, we are just reparameterizing this AB to 0, 1. Okay. So clearly image of gamma 2 is nothing but image of gamma. From here we can see that it is by the definition of gamma 1. Okay. Sorry, by the definition of image. Okay. So reparameterization changes the length of the curve. This is not correct. So let us see the length of the curve. So the length of the curve gamma 1 is nothing but integral over gamma 1 mod dz. Okay, and length of the gamma 2 is nothing but integral over gamma 2 mod dz. So this will be integral 0 to 1 gamma 2 dot t dt, modulus of gamma 2 dot t dt. So this you will get from integral 0 to 1 modulus of gamma 1 dot h of t. Wait a minute. So this is, yeah. So gamma 1 dot h of t and h dash t dt. So what is your h of t? So h of t is equals to u, h of 0 is equals to a, h of 1 is equals to b. So we are just writing this as h of t is equals to u. We are just changing the parameter. So h dash t dt equals to du. Okay. So this will be du and gamma 1 dash u du. So this is again a length of the gamma 1. Okay. So the length of gamma 2 will get length of gamma 1. Okay. So it means that you have a curve gamma, its reparameterization, whatever the reparameterization you will take, its length will be the same. Okay. What is the next problem? C. So let gamma be a curve defined by this for all t belongs to 0, 1. Then length of the curve gamma is equals to 1. So what is this? So this you can directly calculate. So it is just a constant point. So this length will be 0 only. So for any constant curve, the length is 0. So any curve, this is uniquely determined by gamma of 0 and gamma dot t. So gamma dash t for every t belongs to 0, 1. So this is little bit. So this is important. So any curve gamma from 0, 1 to c is uniquely determined by gamma of 0 and gamma dash t for every t belongs to 0 and 1. Okay. So let gamma from 0 to 1, so gamma such that 0 to 1 to c be a curve, and this is again be another curve such that so this is capital gamma. So this one gamma of 0, capital gamma of 0 is gamma of 0, and capital gamma dash t is equals to gamma dash t for every t. So since these two are equal, means this is nothing but a constant addition of this one. So these two differ by a constant, and these are gamma of 0 equals to this capital gamma of 0. So implies that k is equals to 0, and thus these two are equal. So means this actually, so this actually gives you the uniqueness. Okay. So it means that if any curve, so if so what does this statement say? This statement says that if there is any curve which shares the same value, so if you have a curve sigma which is equal to, so that sigma of 0 is equals to gamma of 0 and sigma dash t is equals to gamma dash t, then basically both gamma and this sigma are same, they are not different. Okay. Next thing is, so if gamma t is equal to this is parameterization. Okay, then gamma is continuously differentiable if and only if both this and this are continuously different. So this is a well-known fact. So this is continuously differentiable if gamma dash t exists. So gamma dash t so gamma dot t exists and continuous for all t belongs to this, and gamma dot t is nothing but this one. So this is continuous. It means that this is continuous and this is also continuous. Okay. So what is the next thing? Suppose that gamma 1 and gamma 2 be two curves such that the terminal point of gamma 1 is the initial point of gamma 2. Okay, so this length of gamma 1 plus gamma 2 is nothing but length of gamma 1 plus length of gamma 2. Okay, so how this looks like? So this is nothing but this one. Okay, so you have, suppose gamma 1 is a curve and gamma 2 is a curve. So this is nothing but, so you have a curve gamma 1. So the terminal point of gamma 1 is this, and initial point of next curve gamma 2 will be this one only. So they are attached. Okay, so so this addition is defined like this. So the parameterization of this addition in between this 0 to 2 is defined like this. So from 0 to 1 it is gamma 1t, and now again 1 to 2 you have to parameterize this gamma 2. So this is nothing but t minus 1. Okay, so this is defined in the same. Now this one you can calculate. So length of the curve gamma 1 plus gamma 2 is nothing but integral over gamma 1 plus gamma 2 mod dz, which is nothing but integral 0 to 1 gamma dot t dt plus, oh wait a minute, so this will be nothing but integral over 0 to 2 and mod of gamma 1 plus gamma 2 dot t. Okay, and this you can basically so 0 to 2 you can divide 0 to 1 and 1 to 2. So 0 to 1 gamma 1 plus gamma 2 dot t is nothing but gamma 1 dot t, and 1 to 2 gamma 1 plus gamma 2 dot t is nothing but gamma 2 dot t minus 1. Okay, and so what is this one? So t minus 1 you can take u, so again dt equals to du, so gamma 2, so once you take t minus 1 is equals to u, so at 1 it is 0, 2 equals to 1, so again it is integral 0 to 1 gamma 2 dot u du. So integral 0 to 1 modulus of gamma 2 dot u du. So what is this? This is nothing but the length of the curve gamma 2. So this is integral of gamma 1 plus gamma 2. Okay, so this is true. So this option is also true. Yeah, so okay, so fine. Now let us move towards some problems related to the Mobius transformations, which, so this I included as my assignment problems in my assignment problems. Okay, which I wanted to talk later because I just wanted to first finish all the things. Okay. Okay. So this we know. Okay, so this we have seen that every Mobius transformation has at most two fixed points. Okay, so obviously other than the identity is again a Mobius transformation. So every Mobius transformation T other than the identity has at most two fixed points. Okay, now okay, so this is, so two Mobius transformation F and Z. So this two Mobius transformation F and G are said to be conjugate if there exists a Mobius transformation T such that F can be written as T inverse G dot T. Okay, or G can be or G can be written as I mean, again, it is kind of, or equivalent to T composition F is equals to G composition T. Okay, so let us see the corollary of this one. So if S and T are two Mobius transformations which agree at three distinct points of C infinity, then S and T are identically equal. That is, if Z1, Z2, Z3 belongs to C infinity such that S of Zi is equals to P of Zi, then what we will get? So S inverse T of Zi is equals to Zi. Okay, so this S inverse T is again a Mobius transformation which is having three fixed points. It means that it has to be identity map. So Sz is equals to Tz. Every Mobius transformation which fixes 0, 1 and infinity is necessarily the identity map. Again, again a Mobius transformation can have at most two fixed points. Okay, so it is fixing 0, 1 and infinity. Okay, yeah, so T is a Mobius transform which fixes 0, 1 and infinity, so it has to be identity map only because DZ is an, so the identity map fixes, so the identity map fixes 0, 1 and infinity. Okay, let us look at the next problem. So this is the quite important one. Yeah, so suppose you have given an order triplet. Okay, Z1, Z2, Z3 in C infinity, so extended complex plane. Okay, so the theorem is there exists a unique Mobius transformation which sends Z1 to 1, Z2 to 0 and Z3 to infinity. So this is kind of I mean to say this is kind of what we see in the Riemann mapping theorem. So this is just, we are parameterizing it. Okay, so I mean the way we see, the for the uniqueness we need to put some additional conditions. So here is the condition. So it is on the triplet, so you have Z1, Z1, Z2, Z3, and it maps. So there is a unique map, a unique Mobius transformation which says that Z1 goes to 1, Z2 goes to 0, and Z3 goes to infinity. So it is kind of using the cross ratio. So let Z1, Z2, Z3 is Z3 belongs to C. Then consider a Mobius transformation. This one, we don't know whether it is a, yeah, it will be the Mobius transformation. So Z minus Z2. So this is kind of easy to define. Just you have to make sure. So since Z3 is going to infinity, so Z3 has to be here. Okay, so Z minus Z3 has to be here. Okay, Z2 is going to 0, so Z2 has to be here. So Z minus Z2 and upon Z minus Z3 is clear. Okay, now Z minus Z2 and Z minus Z3 is clear. Now it's sending Z1 to 1. So once you put Z1 minus Z2 and Z1 minus Z3, so okay, so Z1 minus Z2 should be above and Z1 minus Z2 should be below. So to cancel out. Okay, so that you will get 1. So it is easy to define. So to prove uniqueness part, yeah, so existence part we have proved. Uniqueness parts, if one of the points z1, z2, z3 is infinity, okay, so then t of z is equals to this one, and if z2 is equal to infinity, if z3 is equals to infinity. Uniqueness can be proved by using corollary 1. Okay, so this is the corollary 1. Okay, fine. The uniqueness is quite easy. Yeah, again, so this is again like corollary of the earlier result. So z1, z2, z3 and w1, w2, w3 are two triplets, and so disjoint points in C infinity. Then there exists a unique Mobius transformation T such that T of Zi is going to Wi. Okay, so this is again, you just have to compose it with the inverse and you just use the previous theorem. Okay. Okay, so the cross ratio, let Z1, Z2, Z3 and Z4 is in C infinity. Then the cross ratio of Z1, Z2, Z3 and Z4 is the image of Z1 under the Mobius transformation which sends Z2 to 1, Z3 to 0 and Z2, Z4 to infinity. Fine. So next problem is, so if T is a Mobius transform, then it preserves the cross ratio. Okay. So this is the important one. So this is the next problem. So if T is a Mobius transformation, then T preserves the cross ratio. Okay. So let S be a so Z1, Z2, Z3, Z4 is what? Cross ratio of Z1, Z2, Z3, Z4 is what? So this means that image of Z1 under the Mobius transformation which sends Z2 to 1, Z3 to 0 and Z2 to Z4 to infinity. So let S be that Mobius transformation. Okay. So S of Z1 will be the cross ratio and H be a Mobius transformation for this one, this cross ratio, right hand side cross ratio. We have to claim that S of Z1 is nothing but H of T of Z1. Okay. So this we have to prove. So consider this one, S inverse composition H composition T. Now what will be the fixed point of this one? So T sends Z2 to, yeah, so H sends T of Z2 to 1 and S inverse sends 1 to Z2. So this fixes Z2, Z3 and Z4. So it has 3 fixed points. It means it has to be identity map. So again, H composition T of Z is equal to SZ. In particular, H composition T of Z1 is equal to S of Z1. So we have this one. Cross ratios are preserves. In fact, cross ratios are equal of, like suppose you have given two different 4 points, Z1, Z2, Z3, Z4 and W12, W2, W3, W4. These cross ratios are same if and only if there is a Mobius transformation T which sends Zi to Wj. This is again easy to prove. Let us see the proof of this one. Yeah. So Z1, Z2, Z3 and Z4 we have given and W1, W2, W3, W4 we have given. So if there exists T, so we are proving this part. So if there exists a T such that T of Zi is equal to Wj, then by the previous theorem we will get this one. This is easy, okay, this part. Okay, this part is quite easy by this one only. So if a Mobius transform preserves cross ratio, so if there exists a Mobius transform, they will preserve the cross ratio. Conversely, if this one is there, let G be a Mobius transform which sends Z2 to 1, Z3 to 0, Z4 to infinity. So G of Z1 is this, and H be a Mobius transform which sends W2 to 1, W3 to 0, W4 to infinity. So H of W1 is basically W1, W2, W3, W4. Now by assumption, G of Z1 is equals to H of Z1, okay, because the cross ratios are same. So what we have to prove? We have to prove we have to prove the existence of a Mobius transformation which sends Zi to Wi. Now consider H inverse G, okay, H inverse G. So H inverse of Z1 is what? H inverse of Z1 is, so H inverse G of Z1 is nothing but, so what is G of Z1? G of Z1 this cross ratio, okay. So H inverse of this cross ratio is what? just wait a minute. Okay, so H inverse, yeah, so G of Z1 is nothing but the cross ratio, this one, and this cross ratio is nothing but equals to this one by assumption, this cross ratio W1 W2 W3 W4. So H inverse of this cross ratio is what? H inverse of this cross ratio is nothing but W1. Okay, so H inverse G sends Z1 to W1, and similarly H inverse composition G sends ZJ to WZ for all j belongs to 1 2 3 4. Okay, so this is done regarding the Mobius transformations. Mobius transformation maps circles into circles. This is just for a metric space. I have written down it here just for the anything else we left. Yeah, so this is kind of a equation of a circle passing through the origin. So this is kind of so what would be the image of these things under the function 1 by z? Okay, this is just a mere calculations. Okay, so these all things I will upload. So okay, so next thing is, next part is, and this historiography production is fine. Okay, yeah, so we are done with this week 4 assignment. Yeah, so we are done with the week 4 assignment. Thank you, everyone. So we will meet on Sunday, the week 5 assignment. Okay.